Alright, so starting with section 2.4, measures of variation. The most basic measure of variation is range. So we've talked about so far of how or where the center of the data set is, or what's a typical entry for a data set. But now we're going to talk about how spread out is a data set. And you probably remember range from your elementary school days, which is basically the maximum, the difference between the maximum and the minimum. So you just find the largest number and the smallest number, and you subtract the two. But the problem with just subtracting two numbers in the data set is, one, it only uses two numbers in the data set, and two, it can give you some pretty crazy results, especially if you have outliers, right? So, you know, if you're collecting a data set and you have a number that's really extreme and you subtract the maximum minus the minimum, whereas most of the data is probably just in one area, then it can make it seem like the data is more spread out than what it actually is. So that's why we like standard deviation, because every number gets used in the data set. And if you watched my previous video, you'll see that the first thing that we did is we found the deviation of each entry, and this is just simply the difference between the mean of the data set and each data entry. So to find the deviation of an x value, we take x and we subtract the mean mu. But if we just average the deviations, we always get 0. So what we're going to do instead is we are going to compute a quantity called the sum of the squares, and we square each deviation and then add all of those squares together. And when we divide by the number of data entries we have, we end up with a population variance. And to summarize everything, basically we sum together all of the x's minus the mu's, quantity squared, and we divide it by the total number of data entries that we have. That was the population variance, and that is denoted by a sigma squared. And sigma squared, this is actually, you might remember, this symbol is also sigma. So in Greek, this is a capital sigma, and this is a lowercase sigma. So they're both sigma. It's just one's a capital letter and one's a lowercase letter. Like in English, we have lowercase and uppercase letters. Okay, and then the standard deviation is simply just the square root of the variance. And that is a relationship you should be familiar with, that if you take the square root of the variance, we get the standard deviation. Okay? And this is really the main takeaway of this whole entire section, which is that standard deviation is a measure of variation. This means it measures how spread out the data is. If the data is closer together, the standard deviation is smaller. And if the data is spread apart, the standard deviation is larger. All right, so let's go through another example. I'll just rewrite the formula here. And we can summarize this process in 6 steps. We find the mean first. We find the deviation of each entry. We square each deviation. We add to get the sum of squares. We divide by n to get the population variance. And we take the square root to get the population standard deviation. So let's do that on this data set here. So these are salaries of employees at a company, And notice how I have a blank table, and this blank table is going to help us with the process of organizing our work. So sigma is the square root of the sum of x minus mu quantity squared divided by capital N. And the square root is over the whole thing. Okay, so the first thing is if we look in our sigma, we do x minus mu, which is the deviation. So what each column is for is each part in the summation. So x is just simply what are the data values. So I'm just going to list them from smallest, least to greatest. And what I want you to do now is think about what goes here. Well, I kind of did this in the first example. We subtract mu, right? And then we square those, because these are the deviations and these are the squares of the deviations. So see if you can figure out what numbers go in the columns and see if you can actually calculate the standard deviation. So pause it here and try to do that. Alright, so hopefully you work this out on your own, and the first step is finding the mean. And when you find the mean of this data set, you should get 41.5. So we have to subtract 41.5 from all of these. So 37 minus 41.5 is negative 4.5, negative 3.5, negative 2.5, negative 0.5, negative 0.5, negative 0.5, 0.5, 2.5, 3.5, all the way to 47 minus 41.5, which is 5.5. Then we square all of these numbers, so we get 20.25, get 12.25, get 6.25, get 0.25, 0.25, 0.25, 0.25, 6.25, 12.25, 30.25. And then we add all of these together, and this is our sum of squares. And when we do that, we get 88.5. And this is the numerator under the square root. 88.5 divided by how many data points do we have? N? Well, we have 10. And that's the square root of 8.85. So 8.85 has a special name. That is the population variance. But to find the standard deviation, we take the square root of the variance. And we end up with a number that's approximately 3.0. And I'm just going to round to one decimal place. And yes, 3.0 is different than 3. The 0.0 tells you how accurate you are, so it's important to keep the 0.0 if that's actually what you're rounding to. But you want to round to at least one decimal place because my data, once again, is whole numbers, and so you want to be at least accurate as one decimal place further than the original data set, unless directions say otherwise. And that's how we find the population variance, or excuse me, population standard deviation. Okay? So let's do this one more time, but now let's do it with a sample. So if we want to find a sample standard deviation, first of all, this is denoted by a different symbol. Like x bar is denoted differently from mu. X bar and mu are different. So S is a sample standard deviation. And to do this, we still take the sum of each data entry, but instead of mu, what symbol do we use for the sample mean? Because now we have a sample. So we don't use mu anymore, we use x bar. If you remember, x bar is the mean of a sample. And we still square that. And instead of dividing by a capital N, well, it's a sample size, not a population size. So we use lowercase n. And lowercase n, and here's the trick, -1. There's this -1 here in the sample formula. So really, the calculations are all the same. It's just the notation's different, except for that -1. So make sure if you have a sample, read the problem, and from reading the problem, you should know if it's a sample or a population. And if it's a sample, make sure you subtract 1, and we take the square root. You might ask why this -1 is here, and I'm going to post a separate video, a link to a separate video on a website I think does a really good job of explaining why that -1 exists. To actually fully grasp it, you actually need to study statistics a lot more in depth. But for now, I'm just going to leave that to you and just have you accept that -1 exists. Okay, so the -1 is there, and basically all the steps are the same, except we divide by n-1 instead of a capital N to get the sample variance. Okay? So let's find the standard deviation of the heights of 5 random people in this class. And since this part is online, or it's just a video, I can't really get the heights of 5 random people in this class. Okay? So instead, I'm just going to make up some numbers here. So let's see, 67 inches tall, 68, 70, 72. Let's say there's a tall guy at 77. Okay. So we want to find what the standard deviation is. So I would pause the video here. Try to go through the steps of finding the standard deviation. Remember, the sample standard deviation is the square root of the sum x minus x bar, quantity squared, all over n-1, and try to find the sample standard deviation. So hopefully you paused the video and you tried to find the sample standard deviation. The first thing you should have done was find x bar. Okay, so to find x bar, we have to add all of these. We have to add all of these together and divide by how many we have. So let's see, we have 67 plus 68 plus 70 plus 72 plus 77, and we're dividing by 5. So I got 70.8 for my sample mean. And let's subtract that from each of the entries. So this is -3.8, this is -2.8, this is -0.8, this is 1.2, and this is 6.2, I think. Yeah, that looks right. And now we have to square all these numbers. So if we take -3.8 and square it, we get 14.44. Okay, and if we take 2.8 and square it, we get 7.84. This is 0.64. This is 1.44. And the last one is 38.44. Okay, and then we're going to add all these together to get the sum of our squares. Almost wrote mu instead of x bar, right? Which would be a travesty, right? So 14.44 plus 7.84 plus 0.64 plus 1.44 plus 38.4, 62.8. So my sample standard deviation is going to be 62.8 divided by 4, because that's 5 minus 1. There's 5 data entries minus 1. Okay, so we're going to divide that by 4, which is 15.7. So my sample variance is 15.7, but we want to take the square root, which is approximately going to be 3.96. Or actually, if you wanted to do the 1 decimal rule, right, it would be 4.0. As long as you're at least accurate to 1 decimal place, that's fine. But that's my sample standard deviation for this data set. Okay, so that's standard deviation basically. It's a measure of how spread out the data is. So if I were to compare this to my previous example, what's more spread out? My heights of people in my class or the starting salaries of people? Well, the standard deviation is actually 3,000 here because the salary is in the thousands. So my standard deviation is 3,000 here, which is a much larger number than just 4, because here there is no, these are the units, right? So it's, again, this is useful for figuring out how spread out data is and when to compare data sets and figure out how far spread out the data is from itself. So one application of standard deviation is called the empirical rule, and the empirical rule is applied when you have symmetric or bell-shaped data. So maybe you've heard of a bell curve before, and that's basically what the empirical rule is applied to. This is also referred to the 68, 95, 99.7 rule. And yes, you do need to know those numbers because it relates to the rule itself. So let's say in the center of our bell curve we have the mean. We'll call it x bar. Well, one standard deviation away we have 68% of our data. 68% of our data is within one standard deviation of the mean if we have bell-shaped data. If you go out 2 standard deviations away from the mean, so if you add 2 standard deviations and you have bell-shaped data, okay, you now have 95%. So that is the red area and the blue area now. 95%. And then finally, if you go out 3 standard deviations, that's almost all of it, right? In fact, it looks like the curve is touching the axis. It's actually not, but it looks like it is. And that's because that is almost all of it. That becomes 99, I'll have to write it below, 99.7%. So that's where the 68, 95, 99.7 comes from. So once again, 68% of the data is within one standard deviation of the mean. 95 is within 2%, 95% is within 2% or 2 standard deviations, and 99.7% is within 3 standard deviations of the mean. And if you have bell-shaped data, this is very useful. So try to use this concept, this empirical rule, to answer the questions below. So I would again pause it here, read the problems, and try to do them on your own before you see the solution. Okay, so hopefully you paused it and you saw the solution, or you didn't saw the solution, but you have your own solution. So let's see if what you have makes sense. So in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States ages 20 to 29 is 64 inches. So this is the mean. So when you have a problem like this, I would highly advise sketching a small bell curve to help this. And we'll put 64 in the middle because that's the mean. And the sample standard deviation is 2.71. Now we want to find the percent. It says estimate the percent of women whose heights are between 64 and 69.42. So 64 is here, 69.42 is out here. So that's this percentage. And it says assume the distribution is bell-shaped, which is actually a really important sentence because if we didn't know it was bell-shaped or it wasn't bell-shaped, we couldn't use the empirical rule. The empirical rule only applies to bell-shaped distributions. Okay, so what we have to figure out is how many standard deviations away is 69.42. Well, if I take 64 and add the standard deviation, which is 2.71, twice, I get 69.42. So this is 2 standard deviations away. Well, we know from our empirical rule that 95% is within 2 standard deviations. But we can't stop there because this is only one side of the mean. If we look at 95%, that's 95%. The blue area is on each side. So we have to cut that in half because we're only concerned about one side. So 95% divided by 2 is 47.5. So the answer is 47.5% of women in this age group are between 64 inches and 69.42 inches. Okay? So let's do the same thing about the second one. So the mean value of land and building per acre from a sample of farms is $2,400 with a standard deviation of $450. Between what two values do about 95% of the data lie? So again, I would highly advise, and it says assume the distribution is bell-shaped, so I would highly advise drawing a bell shape. We know the mean is 2,400, and 95% is, we know, that is 2 standard deviations, right? 95% is 2 standard deviations. So we're going to add the standard deviation twice. So if I add 450 twice, that is $900 because that's 450 times 2. So I'm going to add $900 this way, which would be $3,300. And I'm going to subtract 900 this way, which is $1,500. So we can say that 95% of the farms have a value between $1,500 and $3,300. And that is one application of standard deviation, the empirical rule. We'll talk about another one next time in section 2.5.